Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a radical equation with complex numbers. We have the square root of z minus 1 equals z, so we need to find a complex number such that when we subtract 1 from it and find its square root, it's going to give us the original number. But wait a minute, which square root are you talking about? Because there are two square roots, right? Are we talking about the principal square root, and which one is the principal square root, so on and so forth? Too many questions. But here's the thing. Let's go and solve it, and you'll see in a little bit why this is not that complicated. All right. So when you have a complex equation like this one or any other equation with complex numbers, a lot of times we replace z with a plus bi. So let's go ahead and start with that. I guess we could call that first method. And suppose z is equal to a plus bi, and a plus bi is actually significant because, you know why? It's the name of this channel, that's why. So if you replace z with that, you're going to get a plus bi minus 1, that's going to equal a plus bi. We're going to proceed with that, but before that, I want to show you something. The graph of these two functions. Square root of z minus 1, as you can see, it's a radical, it's a curve that is concave down, and z is basically a straight line, right? Do they intersect? No, they don't. That's why we don't have real solutions. We don't? Okay. Well, this channel is all about complex numbers, so that makes sense, doesn't it? Let's go ahead and see how we can solve for a and b. Obviously, you would want to square both sides, right? And when you do, you're going to get a minus 1 plus bi. I'll put the real parts together. Right-hand side is going to be a squared minus b squared plus 2abi. Awesome. This should be a general method for most equations because it's very helpful in most cases, especially when you have absolute value in the equation, some conjugates, so on and so forth. A lot of times this is actually going to be very helpful. By the way, some folks are always talking about the polar form. Do you think polar form is also going to be very helpful here? We can also check that out, okay, after this. So now the real parts are equal real parts. So this equals this, and b equals that. Let's start with the second one because that seems easier. B is equal to 2ab. That means if you take out a b, 1 minus 2a equals 0. This gives us two solutions. Either b is 0 or a is 1/2. Now what happens if b is 0? Most probably a is going to be 0, but let's not make any assumptions because we also know that a minus 1 is a squared minus b squared, right? This equals this. So if b is 0, that means a minus 1 is equal to a squared, right? If b is 0, that gives us an interesting case. You know why? Because if you put everything on the same side, a squared minus a plus 1 equals 0, this equation does not have real solutions. Well, wait a minute. A is supposed to be real, right? Exactly. So that's why we don't get anything from here. Well, at least we tried. And now we're going to proceed with this one. If a is equal to 1/2, 1/2 minus 1 is going to be negative 1/2. And then on the right-hand side, a is 1/2, remember? That's going to give you 1/4 minus b squared. Nice. This is quadratic, but only b squared, so that's easy. Put the b squared on the left, put the negative 1/2 on the right, add 1/4 and 1/2, which is going to give you 3/4, right? So b squared is 3/4, which means b is equal to plus minus root 3 over 2. Does that look familiar? That number somewhat looks familiar, right? I mean, you should definitely know that. Think about sine and cosine. Cool. Now, this is a, this is b, but there are two b values, to be or not to be. Allow me to make that joke because it just came up. Anyways, it wasn't planned. So now that means we have two ordered pairs, okay? So it's going to look like this. 1/2 comma root 3 over 2. This is like a kind of like an a comma b. And 1/2 comma negative root 3 over 2. And of course, these are going to give you the z values because this is a, this is b, this is a, this is b. And z is equal to a plus bi or a plus ib. But a plus bi is better because it's the name of this channel. As you know, 1/2 minus root 3 over 2i. So it looks like there are two solutions. And guess which one is the principal square root? It doesn't matter. They're both good. And when you plug them in, you can realize that they both satisfy the equation. Or don't they? I mean, I haven't tested, but I think they should. I mean, you can test it out. Anyways, remember I told you that I was going to try the polar form, right? Next. Maybe we can call that a second method. I don't know if it's going to work. I haven't tried it, but I have trust in you guys because a lot of people want me to use this. So hopefully it'll work. Now, if z is equal to r e to the I theta, right? From here we should be getting, oh, by the way, another thing is, can I just assume that absolute value of z is 1, so I don't have to worry about r? Well, we can't really say that, right, without checking. So if you take the absolute value, I think this is the problem we're going to run into, but I can still try it. The absolute value of the square root of something is the absolute value of z. In this case, I can kind of take out the absolute value, so write this as the absolute value of z minus 1, but inside the radical. Is that an accurate statement, by the way? Something to think about. And when they are equal like this, does that mean the absolute value of z is equal to 1? That's a good question. You can kind of explore it. But what if it's not 1, right? What happens in that case? Well, in that case, we're just going to plug it in, r e to the I theta minus 1, and that's going to equal r e to the I theta. Easy. And then you're going to square both sides again. R e to the I theta minus 1 equals r squared e to the 2I theta. When you square, it just doubles the exponent, right? Cool. At this point, we can go ahead and do this. Put all the r's and thetas on one side and isolate the one. So kind of like this, r e to the I theta minus r squared e to the 2I theta equals 1. And then from here, I could probably take out some stuff, right? Like maybe r e to the I theta, 1 minus r e to the I theta equals 1. Or, let's think about it. Does that mean r is equal to 1? Now, think about it first. If r is equal to 1, then you're going to get something like e to the I theta minus e to the 2I theta equals 1. So if you think about this, that's going to kind of like give me a trigonometric equation. And then, so one of the things you can do is you can expand it, right? So you can kind of write it like this. And again, with the original, let's not make any assumptions like that r is equal to 1. But let's just go ahead and take it from here. So I can go ahead and write this as r times cosine theta plus I sine theta. And then minus r squared times cosine 2 theta. Notice that we doubled the angle, right? Because we squared it. And then from here, you can kind of separate r cosine theta minus r squared cosine 2 theta. That's the real part. And then the imaginary part is just going to be r sine theta minus r squared sine 2 theta. This is a 2, by the way. And that multiplied by I. And the whole thing is equal to 1, which means this is 1, this is 0. And by setting that equal to 0, obviously, you're going to get some theta values, some r values, so on and so forth. Again, this is a very long way to do it. Maybe I just messed it up. Let's go ahead and proceed with the third method. I'm not very good with polar, right? Anyways, we have square root of z minus 1 equals z. Why not just square both sides? Don't worry about any forms. Square both sides. You get z minus 1 equals z squared. Awesome. Guess what this is? A quadratic equation, and we can solve it, right? Z squared minus z plus 1 is equal to 0. And remember, this came up when we wrote z as a plus bi, right? That was one of the cases. But a was supposed to be real. So this equation is well known, because if you go ahead and multiply both sides by z plus 1, that should give you still a valid equation, but you just have to make an assumption that z does not equal negative 1. This gives you z cubed plus 1 is equal to 0, which means z cubed equals negative 1. So we're basically talking about cube roots of negative 1, but z cannot be negative 1. So except for negative 1, because one of the cube roots of negative 1 is negative 1. We don't want that. What about the other ones? First of all, you can write this as e to the power 2, pi I plus 2 pi ni. Of course, when n is equal to 0, you're going to get e to the pi I. Divide by 3, you're going to get pi over 3. And that's going to give you the cosine of 60 and sine of 60, which is what we just found. Remember, the z values are 1/2 plus root 3 over 2i. And then the other one, you're going to add 120 degrees, which is going to rotate it and give you this one in the second quadrant. And then you're going to get the third one, which is not valid because you don't want that to be negative 1, obviously. So we're going to accept the two solutions. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time in another video. Until then, be safe, take care, and bye-bye.